Good day, students. This is Mr. Ridpath, and I'm trying to help you with lesson 3.4, some extra graphing tips for calculus. The thing we're going to really focus on today is horizontal asymptotes. But before I do that, I want to review vertical asymptotes from algebra so that you remember and see the difference in how we approach them in calculus versus how we approach them in high school, pre-calc. All right, if you take a problem, f of x equals 1 over x minus 2, let's say, then in high school we would say, oh, x minus 2 cannot be equal to 0 because that's not in the domain, so x cannot be equal to 2. And then we would say x equals 2 is our vertical asymptote. And then we would just graph it. And we would plot some points and kind of guess what it looks like. In fact, what we would do in high school is we would say, oh, this is the graph of 1 over x, but it is shifted right 2 units, i.e. the asymptote's there. And the graph of 1 over x looks like this. So 1 over x minus 2 will look like that. 1 over x looks like this with the x-axis. And then we would graph it, and that's how we would do it. But if you remember in calculus, what we did is we would say, oh, okay, so x equals 2 is our vertical asymptote, and now we want to decide what's the graph doing, right? So we would take the limit as x approaches 2 from the left side of 1 over x minus 2. And we'd take the limit as x approaches 2 from the right side of 1 over x minus 2. And in this case, if 2 is from the left, we have a sense that it's this denominator is going to be negative but close to 0. Okay? And so we have a positive number 1 divided by a really small number. So this is going to approach negative infinity. And that's what we see there. We see that as it gets closer and closer to the asymptote, the graph is approaching negative infinity. And in the same way, if we're 2 from the positive, the 2 from the positive is slightly bigger than 2. Therefore, this is 1 over a extremely small positive number, the closer and closer you get to 2. And therefore, this graph is approaching positive infinity. Now, if we struggle to see that as negative and positive infinity, this is the one case where using a table can be really helpful. So you do like 1.9, 1.95, 1.99, 1.999, 1.9999. So you get closer and closer to 2 from the left. This is x approaching 2 from the left. And then you would get numbers here, and you would see that this number would be really big, and these numbers would always be increasing really big. So this is one case where a numerical approach tells us what the solution is, okay? And so that's pretty much okay in this case if you want to do that and you're not sure, okay? All right, so that's how we did vertical asymptotes, because we wanted to find out what was the graph doing close to the vertical asymptote. So now what you can see is that we've got to do something similar with horizontal asymptotes. And just so you know, if you have a horizontal asymptote graphs can approach a horizontal asymptote from the top or from the bottom. Above or below is what we often say. And it's not like vertical asymptotes. You can actually cross a horizontal asymptote, be above, and then cross it somewhere, and then approach it from the opposite side. Okay? You can also cross a horizontal asymptote an infinite number of times. So what happens is the graph is approaching it, but it's approaching it by having a big weave, smaller weaves, smaller, and it approaches and it looks like the horizontal asymptote in infinity, even though we cross it an infinite amount of times. So there are lots of situations on this, and let's go and look at some of the problems and some of the theorems that we have to help us out and solve this. All right, so that's a quick review of vertical asymptotes and what happens with horizontal asymptotes. Let's develop the calculus now. Okay, so there are two definitions that we want to cover right now. And the first one is just the intuitive definition of what a function and what an infinite limit is. So what is an infinite limit? All right. And so in doing this, what we see, we just want a function, and we want the function defined either on the interval from a to infinity or from negative infinity to a. So a to infinity means for x greater than a, and negative infinity to a means for a less, or x less than a. Okay, so those intervals. Then our limit is equal to some actual value. And all that means is that the function gets arbitrarily close to this value L by requiring either x go to infinity or x go to negative infinity. So here's what it means graphically. Suppose we take the function f of x equals 1 over x, okay? This is sort of our basic form. As x goes to infinity, right, as it heads down the horizontal axis, what happens to 1 over x? Well, it becomes 1/10, 1/100th, 1/1000th, 1/1,000,000th. So what happens is these values are getting arbitrarily close to 0, to y equals 0, okay? And the next definition says this y equals L is called the horizontal asymptote. And so then as x goes to infinity, since 1 over x gets arbitrarily close to 0, we then say y equals 0 is the horizontal asymptote. And that's what happens. As we go to negative infinity, the same thing happens, even though we approach it from a different direction, from below. All right? And those are the two definitions. One is just intuitively we're getting arbitrarily close to a horizontal line. A horizontal line as x gets bigger negatively or positively. And then we call that horizontal line an asymptote. All right? If that's what happens. Okay? So what we want to do is we want to be able to algebraically think about how to solve these. So that's the next thing. Okay, so let's talk about a theorem. So if r is greater than 0, okay, where r is just a rational number, then the limit as x approaches infinity of 1 over x to the r is equal to 0. And the limit as x approaches negative infinity of 1 over the x to the r is 0. Now this second part has a little note with it. x to the r has to be defined for all x. Why? Because if we're approaching negative infinity, the x values are negative. So if we have 1 over x to the 1/2, right? If that's our function, okay, then it's not defined. Not defined for all x, because x to the 1/2 is the square root of x, and we can't take the square root of negative numbers, okay? So the r's that work are going to be like 1/3, x to the 1/3 power, because we can take cube roots. So no, that's why they say it has to be defined for all x, okay? So this one would be a no. You couldn't take a limit as x approaches negative infinity, but if it was 1/3 power, then you could, okay? And that's the point there. In any case, 1 over x to any power in general, well, not any power, a rational number power, is going to equal 0. And that's how you think about it. So what we want to do is we want to use this fact to help us solve problems, okay? And so the first problem I want to look at, and that's pretty much what most of the rest of this chapter then is about, a couple of little definitions. But let's do a few limits here. So let's do number 10 out of your textbook. Limit as x approaches positive infinity of 1 minus x squared over x cubed minus x plus 1. Okay? Now, what I want to do is I want to get this, or parts of this, into this 1 over x to the r form. Okay? And so the way I do it algebraically is I look for the highest exponent term. And what I see is I see this x cubed term right here. That's my highest exponent term. So what I am going to do is I'm going to rewrite this as the limit as x approaches infinity of 1 minus x squared times 1 over x cubed over x cubed minus x plus 1 times 1 over x cubed. Okay? And notice what I am doing is I am multiplying by 1, okay? 1 over x cubed, 1 over x cubed, so this is legal, as long as x isn't 0, and it's not, because x is going towards infinity, okay? And so when I do that, this changes the form. It becomes the limit as x approaches infinity of 1 over x cubed minus 1 over x divided by 1 minus 1 over x squared plus 1 over x cubed. So now I can take the limit as x goes to infinity. Notice that each 1 over x term has a rational exponent. And so it fits the theorem. And so essentially, I'm taking the limit as x approaches infinity of 1 over x cubed using my limit theorem of sums minus the limit as x approaches infinity of 1 over x divided by the limit as x approaches infinity of 1 minus the limit as x approaches infinity of 1 over x squared plus the limit as x approaches infinity of 1 over x cubed. All right? Now, This now, these are all rational exponents, and the limit as x goes to infinity of that first term is 0, of the second term is 0. In the denominator, it's 1, because that's a constant, minus 0 plus 0. And therefore, we get 0 over 1, which is equal to 0. And so, y equals 0 is a horizontal asymptote. Okay? Now, if I want to think about what happens, I think about what it looks like graphing. And in general, what I would do is to graph, I would just use a calculator. Now, back in the old days, I would think, okay, 1 over a really big number cubed is smaller than 1 over x, right? Over that same big number. So 1 over x cubed minus 1 over x would be essentially a negative number. And then I would look at the denominator, and I'd have 1 minus something less than 1 added to something even smaller than that, less than 1. So it's close to 1, so it's positive. So I would say, oh, this is a positive over a negative, so it's negative. So it's a horizontal asymptote, but it approaches from below. So if I have the horizontal asymptote, as I'm going to positive infinity, I'm approaching from the bottom. And that's how you interpret with the graph. Now, you can just do this with a calculator. I just have the original function, and I would just plug in a large number, like 1,000 or 10,000, and see if it's positive or negative, and that'll tell you if it's above or below. So that's a way a calculator can actually help you to think about it. So I'll do some of this, but you can use a calculator as well. Okay? All right, so there's our first problem. Let's do another couple real quick. Okay, here we go. So the first one, where you have the polynomials, we're going to do it just like the last problem. I'm going to multiply the numerator by 1 over x cubed and the denominator by 1 over x cubed. So I'm multiplying by 1, and therefore I can simplify this, and that'll give me the limit as x approaches negative infinity of 4 plus 6 over x minus 2 over x cubed over 2 minus 4 over x squared plus 5 over x cubed. And that is going to be equal to, these terms go to 0, right, by the theorem. And so we're going to be left with 4 over 2. And so that gives us our limit of 2. Okay? And then we go to the next problem, number 16. Number 16 is the limit as x goes to infinity of x squared over the square root of x to the fourth plus 1. So when you have square roots, you might have to be a little more clever. And so you go, what's the largest exponent? Well, you say the x to the fourth, but then it's inside a square root. And a square root of x to the fourth is 1 over x squared. So the reality is we're multiplying this by 1 over x squared over 1 over x squared. Okay? Except that the 1 over x squared in the denominator is 1 over the square root of x to the fourth. Okay? Now notice that's still 1. So therefore, the numerator, when I multiply it out, I get the limit as x approaches infinity of 1 over, and the denominator, because they're both square roots, I can combine them underneath the square root. And so I'll write that one in. So I'll have x to the fourth over x to the fourth plus 1 over x to the fourth. So this will be rewritten as the limit as x approaches infinity of 1 over the square root of 1 plus 1 over x to the fourth. And now, as x goes to infinity, this last term goes to 0. And so we are left with 1 over the square root of 1, which is just equal to 1. So that would be our horizontal asymptote going to positive infinity. Okay, so I made a little note here. And whenever you see these sine functions with sine of 1 over x, you typically want to make a variable substitution. So let t equal 1 over x, okay? So when x goes to infinity, then the t will go to 0. So that will change this problem to the limit as t goes to 0 of, and this will be sine of t, and then what's the square root of x going to be? Okay, so since t is equal to 1 over x, if we take the square root of 1 over x, that's the square root of t. So that means 1 over the square root of t equals the square root of x. So I'm going to write 1 over the square root of t. So now I've done my variable change, okay? And once I have that variable change, now I can do t approaches 0, okay? And so that gives us 1 over 0 times sine of 0, which is 0. So we get 0 over 0. So now we have to do something different, okay? And so this is not going to work like that. So now we have to go use those trig limits. So let's do that. So this one's a little tricky. And so let me help with that. Let's rewrite it as the limit as t goes to 0 of sine t over the square root of t. And then let's notice that 0 is less than or equal to this. Now, why is that true? Well, sine t varies from 0 to 1 over its whole domain. And so the numerators between 0 and 1, and t is always going to be some number. So this will always be a little bit bigger than 0. Okay? Even though t is getting closer and closer to 0, it's always going to be somewhere between 0 and 1 over some number. So it'll be bigger than 0. And this is always going to be less than the square root of t. Now, the square root of t, just so you know, as t goes to 0, it's going to always be bigger than 1 over the square root of t. And sine t is always 1 or less. So therefore, the square root of t is always going to be bigger than that. So if you have this inequality, then you can use the squeeze theorem. And I know this is kind of rare, but we use the squeeze theorem on sine t over t to prove that limit. So it makes sense that we would use it on sine t over the square root of t. In any case, the limit as t goes to 0 of 0 is equal to 0, and the limit as t goes to 0 of the square root of t is also equal to 0. Therefore, since this is always between those, it gets squeezed to 0, so this limit is equal to 0. And so you've now seen infinite limits that all the limit stuff we've done before can be used. My recommendation, okay, as you look at these problems is Study all examples of how they find limits. You'll see them using conjugates and different things all through the chapter. And so let me recommend highly that you go through and look at each one of those examples so you know how to do it. Okay? Other than that, let's go to the next thing. So for the rest of this lesson, what happens is they give a formal definition in the textbook of an infinite limit. So like we had delta epsilon for regular limits, we actually have, I believe it's called the NM definition for infinite limits. And it's like delta epsilon, you do a proof. Now, my goal is to not make you do proofs. Proofs are not going to be a part of your lives because you are not going to be math majors. And so my sense of that is it's not going to be valuable to you. And so I think we'll skip over that. But there are a number of other types of problems that we are doing in this section and how the horizontal asymptotes apply to graphing. And so we want to look at some of these other problems that exist at this point. Okay? And we will use that to help us do some graphing, do some other types of problems. Okay? Here we go. So problem 38 asks you to find the horizontal and vertical asymptotes of each curve. And then you want to check the work by actually graphing and looking at it. So let's give that an opportunity here. Okay. So I'm going to take the limit as x approaches positive and or negative infinity. I have to do both limits, so I'll write it like that. And in this case, that's going to be 1 plus x to the fourth times 1 over x to the fourth over x squared minus x to the fourth times 1 over x to the fourth, which is going to equal the limit as x goes to positive or negative infinity of 1 over x to the fourth plus 1 over 1 over x squared minus 1. And so with either positive or negative infinity, these two terms right here are going to go to 0. All right? And so I am left with 1 over negative 1 or negative 1. And so the horizontal asymptote is y equals negative 1. So that's what our lesson told us. Now, they also wanted us to find the vertical asymptotes. So I'm going to do 1 over x to the fourth over x squared times 1 minus x squared. And that tells me if x squared equals 0, then x equals 0. And 1 minus x squared equals 0 gives 1 equals x squared. So plus or minus 1 is equal to x. And so those are, so the vertical asymptotes are x equals 0, 1, and negative 1. Okay? And then we can do, in this case, we can do the limits as x approaches 0, 1 or negative 1 from the left or the right. So there's 6 limits to evaluate there. Okay? Of the function 1 plus x to the fourth over x squared times 1 minus x squared. And so we could then go through, so 0 from the right, this means it's slightly bigger than 1, and then the bottom, it's a positive, so this would be positive infinity. If we did 0 from the right, that would be positive infinity. So when we had the asymptote at 0, I would know the graph would be up here. Okay, that's the kind of thing we're trying to figure out where it approaches. Okay, same thing on the horizontal asymptote for graphing. We approach negative 1, whether we're doing positive or negative infinity, but is it from above or below? And that's kind of the trick. So if it's positive infinity, you'll be slightly bigger than 1, and the denominator will be negative, okay, close to a negative 1. So it's positive over a negative, which is positive. So it would be above as you approach positive infinity, it's above. And as you approach negative infinity, it would be slightly less than 1. And that would be from, I believe it's below. Now, that's not the best, but we could check that. And so the idea is on this lesson, you just want to find the asymptotes, okay? Not actually graph it. And then what you do is you graph it to check if you're correct. And so here's the graph. I've graphed it. And for the vertical asymptotes, we can see that we have a vertical asymptote here at x equals negative 1. And then here's the one at positive 1. And then here's the one at 0. And those were the vertical asymptotes. And we can see that the graph is approaching them. So that's a confirm. And then we can also see the horizontal asymptote at y equals negative 1. So that's a confirm as well. Okay? So there you go. That's what you're supposed to do on like problems 35 to 40. Okay, let's go to another problem. So on this problem, they just want you to graph it. They want you to do increasing, decreasing, and then also do the asymptotes. So I want to do that as well. So I'm going to start off with the usual stuff. So the vertical asymptote, okay, is going to be where 1 plus x equals 0, the denominator. So x equals negative 1. So, whoops, negative 1. There we go. So then I take the limit as x approaches negative 1 from the right, and the limit as x approaches negative 1 from the left of 1 minus x over 1 plus x. And I want to be able to evaluate whether that's going to be a positive or a negative infinity, okay? And if I'm negative 1 from the right, this is going to be close to 2. 1 minus x is going to be close to positive 2, but it'll be slightly bigger than positive 2. Whereas the denominator, negative 1 from the right, is going to be a positive number. It's just going to be a positive small number. So this positive over positive, and it's kind of big over very small. So this would be positive infinity, okay? And then the next one down below, and I could do that numerically by actually putting numbers really close to -1 and then see that they get bigger and bigger. Now in this case, -1 from the left, that means we're going to be like a negative, this is going to be 2 on the left. I'm sorry. So -1 from the left, that's like a -1.001. So when we subtract that, we're going to be 2 from the right. That's why I switched that up above there. And then -1 from the left down below, that's like a -1.01. So this is going to be a negative number. So it's going to be negative, but really small. And so that's a positive divided by a negative. So we're going to go to negative infinity there. Okay, so that's the vertical asymptote analysis. So now we can do the horizontal asymptote analysis. Okay, so vertical, horizontal, and the horizontal asymptote will be the limit as x goes to infinity of 1 minus x over 1 plus x. We multiply that by 1 over x over 1 over x. And that will give us the limit as x approaches infinity, 1 over x minus 1 over 1 over x plus 1. So this will equal -1 over 1, which is equal to -1. And if we approach negative infinity, we also get -1 in this case. So I can put plus or minus infinity, and then that's that. So the horizontal asymptote is -1, okay? And then if I want, I can put a really big number in and just evaluate whether we're above or below. So say like 1,000,000. 1 minus 1,000,000 is -999,999. 1 plus 1,000,000 is positive, so it's negative over positive. So if we approach positive infinity, then the graph is going to be like -999,000. So it'll be a -1, but it'll be smaller than the -1, which puts it like -0.999999. So that's actually above. I know, you really have to think about this if you do it this way. And it's worthwhile to kind of ponder it. And so then negative infinity, so like -1,000,000, this will be 1,000,001, and the denominator will be a -999,999. So that'll be -1, but it'll be slightly bigger than the 1, which means it's below on the negative side. Okay? So this is positive and negative signs and signs of numbers, and when you get on the negative numbers, you got to really think whether they're above or below. But that helps me for the graph. I know where that is on the graph. Okay? Now, this was normal stuff. This is the new stuff that we did right there. So the old stuff would be take 1 minus x and set it equal to 0. So 1 equals x. And so f of 1 is equal to 1 minus 1 over 1 plus 1, which is 0. So this is the x-intercept. Okay? And then we can take the first derivative. So we take f prime, and that's equal to 1 plus x times negative 1 minus 1 minus x times 1 over 1 plus x quantity squared. That's the quotient rule. So I simplify that. I get negative 1 minus x minus 1 plus x over 1 plus x squared, and that's equal to negative 2 over 1 plus x squared. So that's our first derivative. And so if we set that equal to 0, there are no values, there are no horizontal asymptotes. No horizontal tangents. No horizontal tangents. However, the derivative is undefined at negative 1. So derivative undefined at x equals negative 1. So negative 1 is a critical point that we need to check for increasing and decreasing. Okay? So I will do that in a minute. The second derivative is going to be, if I rewrite the function as negative 2 times 1 plus x to the negative 2, then I can do it by the power rule. So I get negative 2 times negative 2, 4, times 1 plus x, lower the exponent by 1, times the derivative inside. So I get 4 over 1 plus x cubed. And in the same way, there are no critical points for the second derivative. Okay? Not no critical points. There are no none equal to 0. Let me say that better. Never equals 0. However, it's undefined at x equals negative 1, which is the same point. So now we can do our analysis of the derivative. So the only critical point is negative 1. So let's do the first derivative up here and the second derivative down here. So our test value would be negative 2 in the first derivative. And that would be a negative 2 over a negative 1 squared, which is 1. So the first derivative would be negative there. And then if we plug in a 0 into that, the first derivative is still negative. So the first derivative is decreasing and then decreasing, and not an extrema. It's not a max or a minimum because it decreases and then decreases. The second derivative, if we plug negative 2 into the second derivative, we get 4 over negative 1. It's negative. And then we get, if we plug in 0, we get 4 over 1. It's positive. And so from negative to positive, this is concave down, and this is concave up. But is negative 1 going to be an inflection point? That becomes the question. Well, if you come up and look at the original function, it's undefined at x equals negative 1, okay? i.e. that's a vertical asymptote. So it can't be an inflection point there because it has to be defined in the original function, and that's one of the rules you have to kind of pay attention to. Things have to be defined as well. So now we have all the information. Let's draw the graph, okay? So I'm going to shrink this down. I can see it, so I'll try and restate it as we go. So here's the graph. Let's draw the graph. Okay? And I'll go 1, 1, 1, 1, and then we'll go to 2s. Okay? First of all, we had an x-intercept. So I'll put a check mark. We had an x-intercept of 1, 0. So I'll put that right there. Okay? We had a vertical asymptote of -1. Okay? And we have a horizontal asymptote of -1. So I'll put that as well. Okay? Now, on the vertical asymptote, if we approach -1 from the right, we knew it was going towards positive infinity. So there's that part of the graph. If we were approaching -1 on the left side, we knew the graph was going towards negative infinity. Okay? So something like this would be correct. Okay? On the horizontal asymptote, if we were approaching in positive infinity, we knew it was going to be above the asymptote. And if we were approaching negative infinity, we knew it was going to be below the horizontal asymptote. So there we have that. So now I can add in my concave up and concave down, increasing, decreasing. First of all, the graph is only decreasing. So if I connect these, I got to always be decreasing, and that's what we are. And then we are concave down at less than -1, so we know it's got to be curved like that. And we're concave up at greater than -1. And you see how you can switch from concave down to concave up and not have an inflection point when you have a vertical asymptote there. Okay? And so I think our graph would look like this. Now, what you could do on the left side to make it slightly more accurate is you could say, oh, what's the value of, f of -2, f of -3, and you would plot a couple of points, and maybe those points might plot here and here. So to get a slightly more accurate graph, you would draw that there like that. Okay? And that doesn't mean that that's correct. I'm just saying these graphs are symmetric. And so this space here and here has to be approximately the same. Okay? So I think that's an accurate graph. So let's check it on Desmos. And so you can see now that after I graph it on Desmos, it is correct. I can graph the vertical asymptote at -1 and the horizontal asymptote at -1. And so the only thing I graphed is what the math tells me. Okay? And that's sort of the key to these problems. Only graph what the math tells you. Okay, let's look at one other type of problem. Okay, the last type of problem gives you information and you're to draw the graph from the information. So we'll just work on this slowly, okay? So number 1, f prime of 2 equals 0. This is telling us that we have a horizontal tangent at f prime of 2. F prime of 0 equals 1. So this is just telling us the slope is equal to 1. All right? It then says f prime of x is greater than 0 from 0 to 2 on the axis. So the derivative being positive means that it's increasing here. Okay? The derivative being negative on this interval means it's decreasing. And then they go to the second derivative, and you can see it's less than 0 and greater than 0. So this will be concave down, and this will be concave up on their intervals. And then we have the limit as x goes to infinity of f of x is equal to 0. This is a horizontal asymptote. And then we get this statement right here, f of negative x equals negative f of x for every x. And I don't know if you recognize this, but this means we have an odd function, which means it's symmetric. Symmetry with the origin. Okay? Now, hopefully you remember that. So everything you do algebraically has an interpretation geometrically. So now let's see if we can draw the graph. Okay? So here I go. All right, it looks like my intervals 0 to 2 and greater than 2. So let me do this. So we go 1, 2, and then we went 0 to 4, 3, 4, 5. Okay, so we had a horizontal asymptote at 0. All right, so this is our horizontal asymptote. Okay. We know that we have a horizontal tangent at 2. Okay. Then we're decreasing. So let's see, we're increasing from 0 to 2. But while we're increasing, we are concave down. And okay, so while we're increasing, we're concave down. They don't give us intercepts or anything, so we can go anywhere. So up to 2, increase, we're concave down. And then we're decreasing, and at 2, we get a horizontal tangent. Okay, that makes sense. There's a horizontal tangent. So then we're decreasing and concave down to 4. And then we go concave up and have the horizontal asymptote at 0. Oh, okay. So I think I'm just thinking about it, horizontal asymptote 0. So what happens is I'm going up to some point 2 where I have a horizontal tangent, okay? So I know this is curved like that. And so I don't know how long it is. They don't give me starting values or anything. And then I come down and at 4, somewhere at 4, 1, 2, 3. Oops, not quite there. Okay, I think I got it. What I got, the first drawing I did gave me the shape. Okay, and so now I have the shape, and once I get the shape, then I can go from there. So 1, 2, 3, 4. Okay, so at 2, somewhere at 2, we have a horizontal tangent, okay? We know that the graph is increasing and concave down, then it's decreasing, and somewhere at 4, we're concave down here, it switches to concave up. So this is an inflection point at 4. So this tells me inflection at 4, okay, and maximum at 2. So at x equals 2, we have a maximum. At x equals 4, we have an inflection. And then we had a horizontal asymptote. So it gets close to the horizontal asymptote. Now, the other thing that it tells me is that this function is an odd function, which means it has symmetry with the origin. So I got to come up here, do this like that, but then I have symmetry with the origin. So the other side has to mimic it exactly. All right? And so that's how I end up drawing this other side, is from symmetry. But I kind of guess it on that side. So this was the real work, and then symmetry gave you that because it was an odd function. It gave you the other side. So I think that's the correct graph. Okay? And that's how you do those problems. Those are quite fun, to just take the interpretation and it tells you things. There's a max, there's an inflection, then there's symmetry, which, so I start at 0 and I go up. Okay? And that's it. And this could probably, since concave down, it's probably a little more curved to there. But that would be it. Okay? That's how you think about those. Alrighty? I think that there's other problems, but they're variations on these. So good luck. I'll post the assignment.